On similar grounds as linear polynomial, we will discuss now about a quadratic polynomial. A linear polynomial whose degree is 1 and a quadratic polynomial whose degree is 2 is what we're going to study in the graphical understanding of how the shape of quadratic polynomial would be. The shape of a linear polynomial is a straight line. The shape of a quadratic polynomial is what we're going to discuss here. So let's consider the quadratic polynomial. And the graphical understanding of quadratic polynomial is what we're going to discuss in the session. Now coming to the graphical understanding of a quadratic polynomial, let's take a quadratic polynomial. We all know that a quadratic polynomial is generally denoted in general form as ax squared plus bx plus c. Say for example, where the condition is that a is not equal to 0 and a, b, c are all real numbers. The quotient of this would not be 0 and hence we get belonging to real numbers. This is how I understand the graphical understanding, starting with general form. Now before we start with the graphical understanding, as in the previous session we have discussed that an x-intercept is the intersection of the polynomial with x-axis and y-intercept is the intersection of the polynomial with y-axis. Similarly, it holds for any polynomial considered. So here my x-intercept is what I need to find before I graphically draw the quadratic polynomial. So x-intercept is intersection of this equation p of x. If I take this as y, this is the intersection of y is equal to p of x with x-axis is how I understand the x-intercept. The curve, the polynomial, the quadratic polynomial which cuts x-axis, that intersection points are called x-intercepts. So similarly, my y-intercept is also in the similar definition where intersection of this with y-axis. So when the polynomial cuts y-axis, then the points where the quadratic polynomial cuts the y-axis, those points are called the y-intercepts. Give us the y-intercept values. Therefore, in order to obtain the points where the graph cuts, the quadratic graph cuts x or y-axis is what initially we're going to find. So let's take an example quadratic polynomial and identify how the x and y-intercepts can be calculated for the quadratic polynomial, or for any polynomial the method would be the same. So therefore, to start with an example, let me take a quadratic polynomial y is equal to x squared minus 5x plus 6. Now this is a quadratic polynomial because the highest power here is 2 and it is a non-integral integer, non-negative integer. Therefore, this is definitely a polynomial with each of the coefficients being 1, minus 5 and 6 and the variable is x. So for this quadratic polynomial, taken as an example case, I identify that my first coordinate is 1, the second is minus 5 and the third is 6, and then finally I get this. Now my first initial stage is to find the x-intercept. How do I find the x-intercept for a polynomial, any polynomial? Now, as we have seen, the definition of x-intercept here is the intersection of the polynomial with x-axis. Then clearly the points I obtain in the intersection would be when I substitute y equal to 0, because every point on x-axis is 0. The point on x-axis always is of the form a, 0, where y is always 0. Therefore, in order to obtain the x-intercept, I take y equal to 0, and to obtain the y-intercept, I take x equal to 0. So starting with x-intercept, I start with taking y equal to 0, because the rule says for x-intercept, take y equal to 0. For y-intercept, take x equal to 0. Is reverse way. So x-intercept, I take y equal to 0. So indirectly, I mean my y is nothing but whole of x squared minus 5x plus 6 equal to 0. Now this is where I want to find the factors or the zeros of the polynomial x squared minus 5x plus 6. So in order to obtain the zeros, first I factorize this quadratic equation where I get the factors x minus 2 times x minus 3 equals to 0 is what I obtain when I factorize this quadratic equation. And then finally I get the value of x, which is 2, 3. When each of the factors are individually equated to 0, I get the zeros of the polynomial to be 2 and 3. And indirectly, these are nothing but the x-intercepts. That is, the graph y is equal to this cuts x-axis at the points 2, 0 and 3, 0 is how I understand in the graphical concept. In the graphical concept, y is equal to the quadratic polynomial x squared minus 5x plus 6 is set to cut x-axis at 2 points 2, 0 and 3, 0 because I get 2 zeros of the polynomial or 2 x-intercepts, and these are the points where the graph cuts x-axis. Similarly, let's see the y-intercepts or the points where the graph cuts y-axis. So to start with the y-intercept, as I told with the rule, x-intercept implies take y equal to 0. Y-intercept implies I will take x equal to 0. To start with y-intercept, let x equal to 0. That implies the polynomial y equal to x squared minus 5x plus 6 is simply substituted with x equal to 0. Thus, this reduces to 0 squared minus 5 times of 0 plus 6 is how this gets reduced. And further simplifying this gives me clearly equal to 0 minus 0 plus 6, which is 6. Therefore, this is the value where the graph cuts y-axis. So graphically, I understand with this point that y equal to x squared minus 5x plus 6 cuts y-axis at 0, 6 because my x coordinate is 0 and my y coordinate is 6, which comes here. Here my x coordinate is 2 and my y coordinate is 0, which comes in the second place. Therefore, the graph cuts x-axis at 2, 0 and 3, 0 and cuts y-axis at 0, 6 is how I understand the x and y intercepts. So once I get the x and y intercepts, I randomly take few of the values picked up and then find the corresponding y values. I take some of the x values and find the corresponding y values as a tabular form. So let's see the table. So coming to the table of values, I just pick up a table, this consisting of x and y, which is p of x, and then starting with I randomly take some of the values ranging from negative to positive. Therefore, I start with -1, 2, 3, and 4 and -4, and I'll take the y values correspondingly for this. Now there's no rule that I have to take some fixed values. Randomly you can take any values which are near to the x and y intercepts. So always choose for x intercepts and take the nearest values ranging between 2 and 3 or nearest to 3, outside of 3 or less than 2. So I randomly took some values which are near to 2 and 3, not too far. Do not take 100 or 1000 and then we cannot draw such a big graph with such a huge scale. So let's find the values of y corresponding to each of x as -1, 2, 3, 5 and -4. Now here I have already included two values x equal to 2 and 3 which are x-intercepts in this. So I can easily get these to be zeros because when x is 2, y is 0. When x is 3, y is 0, because the x value of 2 gives me y is 0. X value equal to 3 gives me y equal to 0. So these two being zeros immediately give me the value as 0. Now next, coming to y, when x is -1, I would like to find the value of y. So x equal to -1 implies the value of y, which is x squared minus 5x plus 6, gives me x squared minus 5x plus 6, and this would give me 1. So when x is 5, I substitute x equal to 5 in the given polynomial. I get 5 squared minus 5 times of 5 plus 6, which is nothing but 6. Therefore, when x is 5, my y is 6, as found out here. Similarly, when x is -4, I just work out here. When x is -4, I get y equals x squared minus 5x plus 6. This, on further simplification, gives me 16 plus 20 plus 6, which is nothing but 36, 42. So my y is too huge, which is 42 on the left. Is how I obtain the values. So let me not take such a big value, but I would try to take -2 so that I get a very lesser value. So when I take x equal to -2, then this would be -2 whole square, 5 times of -2 plus 6, which on simplification gives 4 plus 10 plus 6, 20. Therefore, this value would give me the answer as 20. This is what I get as 20 for x equal to -2. Now with these 5 values obtained, each column giving a corresponding point, I'm going to plot that on the real xy coordinate system, and I get, when I join the points, I get the shape of the given quadratic polynomial. So let's see how the shape of quadratic polynomial would be when I plot these points on the real xy coordinate system. Now continuing with drawing the graph, let's plot these points taken with the first point as -1, 13, correspondingly for x equal to -1, y equal to 13 gives me the first coordinate, and then the second coordinate is 2, 0, and the third coordinate is 3, 0. The fourth coordinate is 5, 6, and the last coordinate is -2 times 20. Is how I took the different coordinates. Now in this case, I see that the lowest value of x is -1 and the highest value is 5. So my x-axis will have the scale ranging from -1 to 5, and the lowest value of y is 0. Of course, the lowest value here is 0 for x. For x is this, and the lowest value of y is 0, and the highest value of y is 20. So I need to take a bigger scale because 20 is the highest value. So the scale depends on the values you have in the coordinates.